today we're looking at alkyne, reactions of alkyne, or the chemical properties of alkyne. Okay? We already know that alkynes are those compounds that have carbon-to-carbon triple bonds, right? And they are equally what? Unsaturated, just like alkenes. And they will also undergo an addition reaction, just like alkenes too. Okay? Most of their reactions in alkenes are almost the same, just that the difference lies in the what? In the how many pi electrons that they have, or the pi bond. So, if alkanes are very reactive because of the presence of the double bond or the pi electron, alkynes will be more reactive because alkynes have more pi electrons than alkane. They actually have 2 pi bonds extra and 4 pi electrons, sort of, because each bond contains 2 electrons, right? So, the same reactions, addition reaction, polymerization reaction can also take place, oxidation reaction can also take place there. So let's focus on the addition reactions first, and from there can we look at the oxidation reactions they can undergo, and then probably look at the polymerization reactions. Okay, so the first addition reaction we'll talk about is hydrogenation. Okay, so alkynes can undergo hydrogenation. Now, in the hydrogenation of alkynes, the hydrogenation can be complete, or you can say incomplete or partial. Okay, so for a complete hydrogenation, of an alkyne, you carry out the hydrogenation using your normal catalysts such as platinum, palladium, or nickel. Okay, so if you're using platinum, most times platinum we use a carbon to support the catalyst, right? If you're using palladium, most times you use barium sulfate. If you're using nickel sometimes involves heating the compound together with it. Okay, so now for a complete hydrogenation is simply a hydrogenation that will take the alkyne straight to the alkane. That's a complete hydrogenation. Okay, a hydrogenation that will take the alkyne straight to the alkane. And in order to achieve this, hydrogenation, you have to make use of the catalyst such as platinum in carbon, or palladium in barium sulfate, or you can use or let's just say palladium and then nickel. Okay, any of these catalysts can work, right? Now, example, let's say we have ethyne. Let's carry out this hydrogenation. Okay, let's say we have 2 moles of hydrogen, right? And the catalyst is platinum. This reaction simply means add 4 hydrogens, because 2 moles of hydrogen means 4 atoms of hydrogen, right? 2 moles of this guy means 4 atoms. Add the 4, 1, 2, 3, 4 to this guy. And remember, once you have added 4 things to a triple bond, you now eliminate the pi bonds that are here, the 2 pi bonds. So what I'm going to have here is something like this. Watch. You add hydrogen here, add hydrogen here. Remember, we already have one here already. There's one here. So you add another one here, add another one here. Those pi bonds that are here, you clean it off, you remove it. So ethyne, after hydrogenation completes, will give you ethane. Right? The same thing goes on for any alkyne. And this particular one is called complete hydrogenation. But how can we hydrogenate and get only an alkane? Remember that if you carry out this hydrogenation, the first stage will produce an alkane. Let me show you. If you have let me repeat this same thing I did here now. This same thing I did here. If I'm to do it batch by batch, if I'm to do this reaction step by step, the first hydrogenation that will happen here will form this. The second one will now form this. So hydrogenation, if it is incomplete or partial means that it must stop at the alkane. Remember, this is the ethyne. Remember, your catalyst here is still platinum. This is ethyne. If you hydrogenate the first one, it gives you ethane. The second one will give you what? The ethane we are talking about. Now, most times it is difficult to recover this one. Most times it is difficult to just recover this particular intermediate here because the reaction happens so fast that you can't have time to control it and get to this alkane. Maybe let's say you want to get an alkane from an alkyne. So a man or someone discovered a catalyst we call the Lindlar catalyst. Okay, there's a special catalyst that is meant for stopping this reaction at this alkane. That catalyst is called the Lindlar catalyst. That catalyst is known as the Lindlar catalyst. Okay, so this catalyst is special. It's known for stopping this reaction at the alkane. It inhibits the formation of further hydrogenation. It stops further hydrogenation of this alkane to the alkane. So the catalyst, the component of the Lindlar catalyst is a palladium coated with barium sulfate and then poisoned with what? Quinoline. I repeat, the Lindlar catalyst is palladium that is coated with barium sulfate and then poisoned. The solution is poisoned with what? Quinoline. So this component here, the job, what it does is to stop this hydrogenation at this point, so that no matter, even if you have 2 moles of hydrogen here, there will be no further hydrogenation. The reaction will stop at this place. So this one is what we call the incomplete, or you can say partial hydrogenation. So example, if we carry out this same hydrogenation using this same the same alkane, let's say we have hydrogenation and we are using palladium this time around in barium sulfate and quinoline. Or sometimes they can give you the question like this. They can give it to you in this form. You can just see Lindlar catalyst. Okay, sorry. You see in this form, hydrogenation, even if it's 2 moles, you are seeing here, and you see Lindlar catalyst. These 2 things are the same thing, okay? So if you don't see Lindlar catalyst, you see the component of the Lindlar catalyst. Or they can ask you, what is the product of hydrogenation of a particular alkyne using the catalyst or using a Lindlar catalyst? Okay, so once you have heard about Lindlar catalyst, even though Lindlar catalyst is not the only catalyst that can stop this, there are other catalysts. I think there's one we call nickel dibromide. It can also do this same function of a Lindlar catalyst. So after the class, after this video, you can go and Google catalysts that can also behave as a Lindlar catalyst in hydrogenation of alkyne. So I think there's one we call nickel dibromide. I think it's one of them too. Okay, there are more of them too. So, but this is the most the ones that is being known because I think it was the first that was discovered. Okay, so what this reaction does is to stop this reaction at the alkane. That is, additional reaction will occur only once. Hydrogenation will occur only once. So when it happens, what you're going to have is CH2 double bond CH2. There will be no further hydrogenation. It will stop there. Same as this, CH2 double bond CH2. That's as easy as. Okay? So let's look at the number 2 reaction of alkyne. Number 2 is halogenation. Halogenation. So halogenation simply means addition of what? The halogens, right? So if you are looking at bromination, you are looking at what? Addition of what? Bromine. So let's consider bromination as a case study now. Bromination, that is addition of what? A bromine of bromine. Okay? Halogenation of an alkyne will produce a tetrahalide. Tetrahalide is a carbon to carbon single bond that has 4 halogens surrounding it. Okay? Example, let's look at example now. Example, we have CH3, C triple bond CH. Let's carry out halogenation. Let's say we have 2 moles of halogens like this. So what happens here is that we're going to add the first 2, the second 2 here. Okay? So what are we going to have? CH3 C, halogen the first one, halogen the second one, halogen the third one, halogen the fourth one. Remember, we still have H here. So have you seen that this involves addition of halogens to this point? But the intermediate, there's an intermediate is formed here. The intermediate formed in this reaction is called a vicinal dihalide. I repeat, the intermediate formed in this reaction is called a vicinal dihalide. Let me show you. Okay, so let's carry out the same reaction again, but this time around, let's do it step by step. Let's do the first halogenation. We have adding these two here. We have CH3, C double bond, CH. We add Br, Br. This is a vicinal dihalide. A vicinal dihalide is a carbon that has halogen adjacent to the carbon. Okay, so let's complete the halogenation now. This time around, do it again. You now have this CH3, C, Br, 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 H. So the final product of bromination of an alkyne will give you a tetrabromide. Okay, tetrabromide means a compound that contains 4 bromine. But the intermediate, what you get at the intermediate here, is what we call the vicinal dihalide. Okay, and these vicinal dihalides are very, very important because we use them in making the vicinal chloride. We use it in making PVCs. Okay, polyvinyl chloride. So we use these dihalides to produce some things. It has applications, right? So now, the next reaction we're going to talk about is hydrohalogenation. So you know what this is? This is the addition of what? HX. So this HX, you know them, HCl, HBr, HI. We also have HF, but most of the times you don't use that for this reaction. So we use mainly, in your exams, you see mainly these 3. So the addition of this HX, to an alkyne leads to the formation of a germinal dihalide. Okay, this reaction leads to the formation of a germinal dihalide. I have told you what is germinal dihalide. A germinal dihalide is a carbon that has the halogen on the same side, like this. This is the germinal dihalide. Carbon attaching to the carbon opposite sides, one up, one down. But vicinal is like this. Okay, so at the end of this reaction, we are going to have something that looks like this. That's what I'm trying to say. So first of all, if you are carrying out hydrohalogenation, remember what comes to your head is the Markovnikov's rule, unless you are seeing a peroxide. If you are seeing a peroxide in the reaction, or hydrogen peroxide, it becomes anti-Markovnikov's rule. But without the presence of a halide, just a hydrogen halide in dry ether forms, gives rise to following the Markovnikov. It follows the Markovnikov fashion, right? So now let's quickly look at the reaction now. Let's use an unsymmetric alkane so it will follow the Markovnikov's rule. Let's say we have something like this now. Let's say we are going to look at addition of what? HBr. 2 moles of HBr. Okay? So it could be in ether, which is the solvent. Okay? So for this reaction, the reaction will proceed twice. Is that also? It will go 2 times. So the first addition reaction will follow the Markovnikov's rule. Look at H. This carbon has more H. This one does not have any H. So hydrogen will go to this side. Br will go to this side. So I'm going to have CH3. C. Remember, if you add 2 things, you clean 1 pi bond. So double bond. We have added Br here. Then we have added hydrogen here. Is that not so? Then this is the first answer, not the final answer, because for a complete hydrohalogenation, We must keep adding until all the pi bonds will leave. So let's continue. I'll continue down here. So if we add another HBr, remember we added one HBr here. One HBr to give us this. H goes to this side, Br goes to. So if I go ahead and add another HBr here to this guy, you still follow the Markovnikov's rule. Hydrogen will add to where there is more hydrogen, Br will add here. So have CH3, C, Br. Remember there is a Br here already. So let me just repeat the one that was here. And this will have this. So we add the second Br here, add the second hydrogen here. So have you now seen that at the end of the day, we are having a germinal dihalide. So this is a germinal dihalide. So but the IUPAC name for this compound is, you can say, is 2-dibromo 1,2,3 propane. Okay, but generally we call this kind of compounds a germinal dihalide. Okay, so this is simply what happens. So what happened here is a partial. For the first one, this is a partial hydrohalogenation. When it now completes with the second one, because remember you have to use 2 moles of this guy, 2 moles of, so one of these will react with this, one of these will react with this again, so that we can have this. So this is what we call hydrohalogenation of alkyne, which forms a germinal dihalide.